Bonsuelo mathletes. Okay, this is going to be kind of a long one. We're going to be talking about rational function graphs. Okay, first of all, let's figure out, and I've defined this before, but let's figure out what a rational function is, because you should be able to, know what the equation looks like, and then how does it graph. So first of all, I've given you this before, but what's a polynomial? Has a whole number exponent on the variable. What's a rational expression? It's a fraction where you have a polynomial in the numerator and a polynomial in the denominator. Okay. Well, we're kind of getting to the point now where we have a fair number of equations that we've graphed. So the first thing we graphed was a linear, this year, this was the first semester, a linear equation. That's a polynomial of degree 1. That was chapter 2. Okay, quadratic, which was chapter 4, is a polynomial of degree 2. That makes a U shape or a parabola. Absolute value, that makes a V. A radical equation, that's kind of like a half parabola on its side. And then the first one that we did of this semester are polynomials of degree 3 and greater. Okay, so what's the basic plan for a rational function? Again, it's a fraction with a polynomial in the numerator and a polynomial in the denominator. Okay, first you're going to find domain and wholes. Second, asymptotes, whatever that is. Third, intercepts. Fourth, you may or may not have to use the limited XY table to fill in gaps in the information. So basically it's domain and wholes, asymptotes, intercepts, and maybe a limited XY table. Or I could even reduce this to a little bit later. I reduce this to wholes and asymptotes, intercepts, limited XY table. But you still need to find the domain. Okay, so let's first of all start, let's just take one of these at a time, and, we need to take this kind of slowly. So domain. For any fraction, the denominator may not be 0. So how do you find the domain? You basically just set the denominator not 0. So we have x squared plus 9x plus 20 is not 0. So x can be anything else other than what would make the denominator 0. Well, how would you solve this? The same way you'd solve it as if it said equal to 0. Okay, so we have x times x gives us x squared plus 5. And plus 4 gives us 20 and 9 in the middle. So x is not negative 5 and negative 4. So if that's what it's not, that's what's excluded from the domain, then what is the domain? The domain is this, everything else. So we start at negative infinity and go to negative 5. And then we skip over the negative 5 and start up with just on the other side of the negative 5 and go to negative 4. And then we skip over the negative 4 and go to positive infinity. Okay? So this right here is what's excluded from the domain. X cannot be negative 5 and negative 4. But this is then what the domain actually is. It's everything but that negative 5 and negative 4. Okay, let's take a look at number 2. Again, we're going to take the denominator and say it's not equal to 0. Fine, so let's factor it. So what times what's going to give us x squared? X times x. What times what's going to give us 6? Oh, let's try a negative 3 and a negative 2. Fine. Okay, so x cannot be 3 and 2. Okay, so then what's the domain? Okay, well, we're going to start with negative infinity, and then what's it go to? It doesn't go to it doesn't go to 3. It goes to 2, because 2 is smaller than 3. Then you skip over the 2, and you go to 3. Then you skip over the 3, and you go to positive infinity. Okay, that's just to find the domain. Okay, And there's a lot here, so I'm going to go pretty quickly. You might have to listen to the video, back it up a little bit, and listen again. So let's go on to holes then. What's a hole? It's like a missing part of the graph. In other words, I'm just going to kind of draw some stuff and then just, but don't draw any of this. Okay, there's a line. That's a line with a hole in it. A hole is just a missing point if you want. Okay? So that's generally what I mean by a hole. Not even generally, it is what I mean by a hole. If you have a parabola, there you go. What's a parabola with a hole look like? It's a parabola with a point missing. Okay, now the question is, how do you find these things? How do you find where there's a hole in the graph? Okay, what you do is if a denominator factor cancels completely out of the problem, you have a hole at that value of x. So let's take a look at this one. Okay, so what we're going to do first is simplify the fraction. And by the way, you should always find the domain first. Okay, so the domain here, or I'm going to say what's x cannot be -3. Now that's not the domain, it's what is excluded. But of course, then the domain would be -infinity to -3 and then -3 to positive infinity. Anyway, let's factor this. So we have 2x times x. Okay, and then what's going to give us -3? Probably +3 and -1. And then on the bottom, we just have x plus 3. Okay, so what happens? These cancel. Did that factor x plus 3 go away completely? Yeah, it's no longer there. So there is a hole at an x value of -3. Well, how do you find the y value? We'll get to that in a second. Okay, so what do we have left? We have g of x equals 2x minus 1. All right, so we're going to graph g of x equals 2x minus 1, which is a line. Well, where's the y-coordinate of the hole? Okay, what we're going to do is we're going to find the point that would be on this at an x value of -3. Well, how do you do that? You plug in -3. So we have 2 times -3, and it's got to be in the simplified equation, -1, because if you plug it into the non-simplified equation, it won't make any sense. So that gives us -7. So where's the hole? There's a hole at -3, comma -7. So we're going to end up with a line, and that's going to be a line that has a hole in it at the point -3, comma -7. Okay, so how does this thing look? All right, so first of all, here's the work for this problem right here. Okay, so what it is going to be is g of x equals 2x minus 1 with a hole at -3, comma -7. Okay, fine. Well, okay, let's graph this first thing. Well, 2x minus 1 is just a line, so we go down to -1, and then we go up 2 and over 1. And we draw the graph. Best you can. Okay. Well, how about this one? Well, we do the same thing. You go down 1, you go up 2 and over 1, but I'm going to put the hole in, and the hole's at -3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, right there. So what we're going to do is draw the graph. Only it's got a hole, it's got a missing point. So they're the same. Number 1 and number 2 are the same. The only difference is there's a point missing, and that point is at -3 comma -7. And again, we did the work for it up here. Well, that's what a hole is. It's just a missing point. Okay, having said that, let's find the holes. Okay, so what we're going to do is factor these. So this is going to be x, plus 4, x plus 3. And then this is going to be x plus 4 and x plus 5. Okay, so the x plus 4 is canceled. Did it cancel away completely? Yes. So there's a hole at -4. Now, how do I find the y coordinate? I plug it into the remaining equation. So we have -4 plus 3 and -4 plus 5. So it's -4 all over. That's -1 over 1, which is -1. That's where the hole is. So however you graph this thing, and I haven't shown you that yet, you will have a hole at -4 comma -1. Okay, this one, number 2. We'd have x plus 5 and what, x minus 2. On the bottom, we have x plus 7 and x minus 4. Okay, nothing cancels. There's no hole. So however you graph this, and we'll get to that eventually, there isn't going to be any hole in it. Okay, this one. We have x plus 5 and x plus 3. And this is x plus 3. You can write x plus 3 quantity squared if you like, or I'm just going to write x plus 3 times x plus 3. Okay, so the x plus 3's cancel. Is there still an x plus 3 in the denominator? Yes. So the x plus 3, all the x plus 3's didn't go away, so there's no hole. The factor, there can't be any factors that look like that. Okay, it has to get rid of all of the x plus 3's in the denominator. Okay, here. You have x plus 3 times x plus 3. And here we have x plus 5 times x plus 3. Okay, let's cancel. Did I get rid of all the x plus 3's in the denominator? Yes. Okay. So there's a hole at -3. Now, how do I find the y coordinate? I plug in the -3 into whatever's left over. So we have -3 plus 3 all over -3 plus 5. And that's going to give me -3 comma 0. Now, you may be asking, so that's where the hole is. You may be asking, well, what about, on this first problem, what about the x plus 5? On the second problem, what about the x plus 7 and x minus 4? On this problem, what about the x plus 3? And on this one, what about... I'll get to that eventually, okay? Right now, I'm just looking at what makes a hole. And what makes a hole is any denominator factor that goes away completely. In other words, you have no more factor that looks like it. So notice here on number 3, we got rid of one of the x plus 3's in the denominator, but there's another one. In number 4, problem 4, we got rid of there are no more x plus 3's in the denominator. Okay, that's why there's a hole there. Okay, now, what's an asymptote? So they're going to be vertical asymptotes and horizontal asymptotes. There are two types, okay? But what's an asymptote in general? An asymptote is a line. Now, it's not part of the graph. It's just something we're going to use to kind of sketch the graph, in which the graph approaches that line, but it does not reach it. In other words, this is what happens. You have something, and I'm going to dash it because it's not, I'm just listen to this, don't draw it. And the graph is going to keep getting closer and closer, but it's never going to reach it. Now, you could say to yourself, how is that possible? Well, let me show you something. And don't write this down, just listen. Okay, let's say we have this. And I'm going to start here. And each time, I'm going to move that point halfway to the line. So I'm going to go halfway to the line. Then I'm going to go halfway. Now I'm going halfway from the line from where it is now, which is right there. Then I go halfway from where it is now, which is right there. Then I go halfway from where it is right now, which is right there. And notice if I keep going halfway to the door, or to the, in class I'll talk about it relative to a door. If I go halfway to that line, I can never reach the line. But I'll also always be approaching the line. So I will approach the line, always be approaching it, but never reach it. Okay? And again, in class, it's a lot easier to explain it. Okay, so an asymptote is a line which is not part of the graph, in which the graph approaches but does not reach. Now, the two types are vertical asymptotes and horizontal asymptotes. We're going to talk about vertical asymptotes first. Okay, wherever a function is undefined and there's not a hole, okay, you have a vertical asymptote. So for instance, going back up into these examples, remember it was like, well, what happens to the leftover x plus 5, the x plus 7, and x minus 4, the x plus 3, the x plus 5? What happens to those? They become vertical asymptotes, okay? So providing something does not become a whole, anything that makes the denominator become 0 will be a vertical asymptote. So let's take a look at these. These are pretty much the same thing we did before. We have x plus 4 and x plus 3. But here I'm only looking for the vertical asymptotes. Okay, here we have x plus 4 and x plus 5. So what happens? The x plus 4's cancel. That's why, remember before, we had a hole there. But I'm not asking for the holes this time. I'm asking for the vertical asymptotes. So whatever's left over, wherever the denominator makes the denominator 0, which is x plus 5, okay. Now, a little discussion of, how can I put it, like notation here. A vertical asymptote, when I find the domain, I say x plus 5 cannot be 0. Why? Because x plus 5 can't be 0. But when I'm finding the vertical asymptote, I want to know what is the equation of the vertical asymptote. So I solve for where x plus 5 equals 0. Now, the graph is not equal to 0, okay, at this value of x plus 5. But the vertical asymptote, which is not part of the graph, is at x equals negative 5. And again, when I start graphing these for you, I hope it'll make a little more sense. Okay, let's take a look at this one. So this would be at x plus 5 and x minus 2 all over x plus 7 over x minus 4. And just like before, there were no holes here. Okay, this gave us a hole, right? So there was a hole for that, but what I asked for was the vertical asymptote, which is x equals negative 5. Okay, well, there are no holes here. So what are the asymptotes? X equals negative 7 and x equals 4. They're vertical lines that the graph will approach but not reach. Okay, in this case, we have x plus 5 and x plus 3 all over x plus 3. And again, you can put x plus 3 squared if you like. It's not that big of a deal. Okay, well, does that give us a hole? No, because we still have the x plus 3 left over. So that will give us a vertical asymptote. Okay, in this case, we have x plus 3 times x plus 3 all over x plus 3 times x plus 5. Okay, these cancel, and the x plus 3 goes away entirely out of the denominator. So just like up here, we had a hole, right, on number 4. But I didn't ask you for the holes here. I asked you for the asymptote. And what's left over after you cancel? x equals -5. That's a line that is not part of the graph, okay? But it's something that the graph will approach but not reach. Okay, that's how you find a vertical asymptote. Now, what's a horizontal asymptote? Now, there's a lot of theory involved in this that I'm not going to get into, okay? But a horizontal asymptote describes what happens to the graph at the extreme far right and far left, okay? For that reason, since it only describes what happens at the far right and the far left, a graph may cross a horizontal asymptote, okay, when it's not at the far right and far left. Now, a graph can never cross a vertical asymptote, and I've stated that before. Okay, well, there are three possibilities, and it's based on the degree of the numerator versus the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is always y equals 0. And again, there's a lot of theory behind that, which I'm not going to get into. If you want to come and talk to me about it, I'd be happy to talk to you about it. Next is where their degrees are equal, and the horizontal asymptote will be the ratio of the leading coefficients. I'll show you an example of that. And the numerator degree being larger than the denominator degree, okay, we're going to do that, or you're going to do that next year. Okay, so let's look for the horizontal asymptotes. Okay, first of all, we want to factor this because we want to see if anything cancels, et cetera, et cetera. Okay. Doesn't even look like the numerator factors at all. So I guess we just don't have to worry about it. Okay, well, what's happening? We're looking at this because nothing's going to cancel, okay, because the numerator doesn't even factor. But all we're concerned with is the leading term, okay? Since the degree of the top is the same as the degree of the bottom, we take the ratio of the leading coefficients. In other words, we write a fraction, and that fraction just has the leading coefficients. The leading coefficient of the numerator is 1 because it's 1x squared, and the leading coefficient of the denominator is 2. So the horizontal asymptote is a horizontal line at y equals 1/2. Okay, in this case, the denominator doesn't factor, so we're not going to be able to simplify it. And since the degree of the numerator is less than the degree of the denominator, it's just y equals 0. You just have that memorized. Okay, number 3, nothing factors and cancels. So we have the degree of the leading term on top and the degree of the leading term on bottom. The leading term being the largest exponent term. So 8 is not the leading term in the denominator, -3x is. So this is y equals 5 over -3, or you could say -5/3. So it's a horizontal line at -5/3. Okay, now, I just don't want to mislead you. I've said I'm not going to ask you where the degree of the numerator is larger than the degree of the denominator. But remember, okay, you've got to look for a whole first. See, on number 1, the numerator didn't factor, so there isn't going to be any whole because nothing's going to cancel. Number 2, the denominator doesn't factor, so there isn't going to be any whole. Nothing's going to cancel. Number 3, nothing cancels. So number 4, we've got 2x and x, and then +3 and -1. And then on the bottom, we have x +3. Well, those cancel. That gives us a whole, all right? But what's this thing graph as? It's a line. It's just a line with a hole. Okay, and we did this before. It's -3 comma something. Okay, so when I'm saying here, right up here, that the numerator degree is larger than the denominator degree, that you'll do it next year, that's if it doesn't give you a whole. Because here, notice It's just 2x minus 1. You're not even talking about anything other than a line with a hole. Okay? Now, what I mean by what you'll do next year is, let's say the bottom was x plus 2. Well, then nothing would cancel. I'm not going to give you that this year. That's quite a bit more complicated. Okay. Now, this, remember, a graph cannot cross a vertical asymptote. But as long as you're not out at the far right and far left, you can cross a horizontal asymptote. Okay. So what we're going to do to see if it crosses is we'll take the original equation, the simplified one, and the equation for the horizontal asymptote, and treat it like a system of equations. Okay? So let's take a look at an example. All right, first of all, what's the horizontal asymptote? That's going to be, so they're both to the first power, so it's y equals 5. Okay, that would be the horizontal asymptote here. Well, what I'm going to do is I'm going to take this 5 and I'm going to substitute it in for f of x, because those two things are the same. F of x and y are the same thing. So I'm going to say 5 equals 5x plus 7 over x minus 9. Now, what do I have? I have a fractional equation. I get rid of fractions. So I'm going to multiply both sides by x minus 9, and we get 5x minus 45 equals 5x plus 7. And then you'd subtract the 5x, and you get negative 45 equals 7. Well, where does negative 45 equal 7? It doesn't. Therefore, there's no solution to that equation. The graph does not cross the horizontal asymptote. Okay, now let's take a look at this one. We have x plus 5 all over x plus 7 times x plus 1. Okay, nothing cancels. So the horizontal asymptote is just going to be y equals 0, right? Because the degree of that is less than the degree of that. But we had to check, first of all, to see if something canceled. All right? All right, so what do? We take 0. Remember, this is y and this is y. So we take 0 and set it equal to x plus 5 all over x squared plus 8x plus 7. And now it's a fraction. We multiply both sides by the lowest common denominator, and you get 0 equals x plus 5. And x equals negative 5. Therefore, the graph crosses, because notice we got a value for x here. The graph crosses the horizontal asymptote at negative 5, 0. Because negative 5 is the x coordinate and 0 is the y coordinate. And again, right now I'm just having you find stuff. Let's go back and see what's the general plan. The general plan is this. Where are we looking here? Okay. Way back at the beginning. Okay. Domain, I've shown you how to find that. Holes, I've shown you how to find that. Vertical and horizontal asymptotes, I've shown you how to find those. Intercepts, you should already know how to find those. We've been finding intercepts pretty much the whole year. And then we're going to draw whatever we can, okay? So we've looked at kind of like the parts, domain and holes, vertical and horizontal asymptotes, and the intercepts, you should already know how to find those. So let's take a look then at some examples. So this is all the preliminary stuff, how to find those things. Okay. All right. A lot of stuff there. Okay, let's go for it. Okay, so first of all, this is x plus 3 times x plus 1 all over x plus 2 times x plus 1. Okay, what's the domain? And I'm going to write the domain as in terms of what's excluded. I'm not going to write the domain really as it is. But notice these x plus 1's cancel. Well, so x cannot be -2 or -1. But what you get at -1 is a whole, because the x plus 1 canceled away completely. Okay? So the whole is at an x value of -1, and to find its y value, you substitute -1 into the remaining the equation that's left over. -1 plus 3 and -1 plus 2. So that's -1, comma, what would that be? 2 over 1. Okay. Let's look at the vertical asymptote. Remember, the vertical asymptote is what's ever left over on the denominator. So that's x equals -2. The horizontal asymptote is we only look at what's left over. We don't worry about, what we already canceled. That's just a whole. Okay? So the numerator degree and denominator degree are the same. It's 1x over 1x. So it's y equals 1 over 1, which is the same as just y equals 1. Okay. For the x-intercept, remember, how do you find an x-intercept? You put 0 in for y. Okay? So we have x squared plus 4x plus 3 all over x squared plus 3x plus 2. Okay, we have a fraction. Multiply both sides by the common denominator and get rid of fractions, and you have 0 equals x squared plus 4x plus 3. So let's solve that. X plus 3 and x plus 1. So your x-intercepts are -3, 0, and -1, 0. Okay, fine. Okay, and your y-intercept. For your y-intercept, remember what you're going to do is you're just going to plug in 0 for x. And if you plug in 0 for x, the numerator just becomes 3, and the denominator just becomes 2. Okay, let's plot all this stuff and then see what we can draw. Okay, so first of all, we have a hole at -1, 2. Fine. Vertical asymptote at x equals -2. So our graph cannot cross that. Horizontal asymptote at y equals 1. And we may or may not cross that. An x-intercept at -3, 0. And a y-intercept at 3/2, 0, 3/2. Now, here's the deal. We can look to see if this is going to cross the y-intercept. Sometimes, the horizontal asymptote. Most of the time, you probably don't need to bother. Okay, that's why I called it a bonus. All right, but think of it this way. As I go from this point here, that one, to the left, well, remember, what's an asymptote? Something the graph approaches but does not reach. So it's going to approach. Now it's drawing a line, which is not what I want. Okay, it's going to approach the asymptote but not reach it. And from that same point, as it goes to the right, it's going to approach the vertical asymptote, but not reach it. It can't cross it. Okay, how about over on this side? Okay, well, from that point, the point that's actually there, okay, the one that's on the y-intercept, as we go to the, let's go to the left first. We're going to approach the asymptote, but not reach it. And we also have to skip over the hole. So what we're doing is have something like that. And then as we go to the right, it looks like that. Now, every graph we've made before always looks like the same thing. A linear equation always looks like a line. A quadratic equation always looks like a parabola. Absolute value always looks like a V. Square root always looks like a half parabola on its side. But this is like what they most typically look like. But quite frankly, they can look like a bunch of different things. Okay? So all we can do is go through examples and see, what it might be. Okay, here. Well, nothing factors and cancels, so there's no hole. Okay, we have the vertical asymptote at x equals 1. The horizontal asymptote. Now, notice these x and 2x have the same degree. They're both just x. So we take a ratio of the leading coefficient, and we get y equals 2 over 1, which is 2. The x-intercept, okay, we're going to put 0 in for y, and we get 2x plus 3 all over x minus 1. Clear the fraction, and we get 0 equals 2x plus 3, and x equals negative 3 halves. So we get negative 3 halves, 0. Okay, the y-intercept. If you stick 0 in for x, you'll get 3 over negative 1, which is negative 3. Okay? Oh, by the way, I just want to point out, notice on this one, number 1, we didn't really need any extra points by XY table. Sometimes you do, sometimes you don't. Let's see what happens here. Okay. Oh, you know what I kind of blew here? Domain. Okay, x is not going to be 1. So I'm going to have every x value represented except for 1. Okay? So let's see, the vertical asymptote is x equals 1. So the graph is not going to go there. The horizontal asymptote is y equals 2. Okay, the x-intercept is negative 3 halves, 0. And the y-intercept is 0, negative 3. Okay, well, from that point, as we go to the left, hopefully it's kind of obvious you're going to go up and, well, it may not be obvious, but we're going to approach the asymptote but not reach it. As we go to the right, it's going to go down towards the asymptote but not reach it. Okay? Now, is that the entire graph? No, it's not, because notice we're missing the whole right side. So we don't have anything over there yet, but we've got to get something. This is where you're going to make an XY table. Okay? Now, you probably don't need much. And what number would I plug in? I'd plug in 2, just the one closest to the asymptote. So let's plug in 2. So you get 2 times 2 plus 3 all over 2 minus 1. So that gives you what? 7 over 1. So it's 2 comma 7. So we have 2 comma 1, 2, 3, 4, 5, 6, 7. Now, from that point, as you go to the right, it's got to go up. Okay? Because if it goes down, it would be crossing the horizontal asymptote. And from that point, as it goes to the right, It's got to approach the asymptote but not reach it. So that 1 point is good enough, for a decent sketch. Okay? And again, you may need to go back and, look at the video a little slower than I'm actually talking. But okay, so let's take a look at this one. So we're going to find the domain first. So we have x minus 4 times x plus 1. Okay, there's no holes. The domain, x can't be 4 and negative 1. And again, I'm not going to write that out in interval notation, but you should be able to if I ask you to. Okay, so the vertical asymptote is whatever the denominator is. X equals 4 and x equals negative 1. The horizontal asymptote, well, the degree of the numerator is less than the degree of the denominator, so the horizontal asymptote is just going to be y equals 0. Okay, the x-intercept, we're going to put 0 in for y. Okay, let's multiply and get rid of fractions. So the x-intercept is 2, 0. And the y-intercept. The y-intercept, we're going to plug in 0 for x, and we get negative 2 over negative 4, which is y equals 1/2. Okay, so that's going to be 1/2, 0. Okay, so let's plot that and then see what we need to do. Okay, so we have x equals 4. X equals negative 1. Y equals 0. Okay. Then we have no holes. The x-intercept is 2, 0, right there. And the y-intercept is 1, sorry, that's wrong. It's not 1/2, 0, it's 0, 1/2. So it's 0, 1/2, which is right about there. Okay. Well, obviously, as we go, or I hope it's obvious, as we go from this point to that point, we're kind of going up. So as we go to the left, we're going to go up. And then we just continue going up. And as we go from that point to the right, well, notice it's going down, so we continue going down. And we can't cross the asymptote. Now notice, we cross the asymptote, the horizontal asymptote, right there. That's why I said you probably don't need to worry about calculating whether we cross the horizontal asymptote or not. It'll kind of just happen, when you find the other information. Okay? Now, is that the whole graph? Well, no. Because we've got this whole section over here on the right that we don't know what's going on, this part over here, and we've got this whole section over here on the left that we don't know what's going on. So we've got to find those. So how are we going to do that? You guessed it, XY table. Okay, and I'm not going to show all the calculations. Okay, well, let's plug in negative 2, because that's on the left, right next to the asymptote. Okay, so negative 2 will give us negative 4 all over. And if you plug in negative 2, you'll get 4 plus 6. So I'm plugging it into the denominator, minus 4. So that gives us what? Negative 4 over 6, which is negative 2/3. Okay? So we'll plot negative 2, negative 2/3. It's right about there. Well, what's going to happen from there? Well, we can't cross the asymptote because I know I don't cross, the x-intercept. The only x-intercept is 2, so I don't cross the y-axis, and I certainly don't cross the vertical asymptote. So, not the y-axis, but I don't cross the x-axis because there's only one x-intercept. So we're going to approach the asymptote, and going the other way, we're going to approach the asymptote. Okay, so that takes care of the left-hand side. Let's plug in, 5 for the right-hand side. And what do we get? 5 minus 2 is 3. And on the bottom, we get 25 minus 15, and then minus 4. Okay, so that's what, 6? Well, sorry, 3 6, which will be 1/2. Okay? So that's 3 over 25 minus, that's 3 6, which is 1/2. Okay, so we have 5, 1/2. And what's going to happen there? This will go towards the asymptote, and going this way, it'll go towards the asymptote. So obviously, this looks totally different, okay, than either of these two examples. These two examples are like what they pretty much typically look like, but you can have them look like all sorts of different things. And remember up here, gosh, what did we have? I'm going to go way up for a second. This one was just a line with a hole, right? Started out as a fraction, but it ended up to be just a line with a hole. So obviously that looks totally different than these ones we're doing now. Okay. All right, so let's take a look at this one. So we have x plus 3 times x minus 2, x plus 2. Okay, there's no hole or anything. All right, so the domain is x can't be 2 or negative 2. Fine. Vertical asymptotes are x equals 2 and x equals negative 2. Again, I want to point out, as the domain, x can't be 2 or negative 2. But as the vertical asymptotes, the equation of the line, it's x equals 2 and x equals negative 2. So be very careful what the question is. Am I asking for the domain or the equation of the vertical asymptote? Okay, horizontal asymptote. The degree of the top smaller than the bottom, so it's y equals 0. Okay, let's look for the x-intercept. The x-intercept, I'm going to set y, put 0 in for y. Okay, get rid of the fractions. Multiply both sides by the common denominator. So we have x equals negative 3, so we have negative 3 comma 0. Okay, and then the y-intercept, if you plug in 0 for x, okay, you're going to get 3 over negative 4. And we'll see, we may or may not need your unlimited xy table there. Okay, so we have x equals 2, x equals negative 2. Okay, we have the horizontal asymptote at y equals 0. An x-intercept at negative 3, so it looks like we're crossing the the horizontal asymptote. And then the y-intercept is 0 comma negative 3/4. So we have 0 comma negative 3/4. Now, let's take this middle point, the one right there, first, okay? Now, remember, this graph doesn't cross the x-axis anywhere between these two vertical lines. So somehow it's going to just be going down. Okay. We'll take the left in a second. Let's go for the right. We have nothing over here on the right as drawn right now, but we do know there's graph over there. So we'll just plug in 3, which is right next to the asymptote, and that'll give us 6 over 5. So we have 3 comma 6/5, and then it probably looks something like this. Okay? Now, here's the problem with the left, this point right here. I don't know if the graph, I'm going to draw some stuff, but don't you draw it, okay? I don't know if the graph is going to be coming like this and then go through it and go down, or is the graph going to be coming like this and go through it and go up? Okay, so here we need to find another point. Let's plug in -4, okay? So if we plug in -4, we get -4 plus 3, and the numerator is -1, and then -4 quantity squared, 16 minus 4 is 12, so -1/12 is some little tiny negative. Okay, so what's going to happen? If it's passing through, it's got to come from the top and go through the bottom. Now, here's the weird part. Notice the graph at this point is going down. Well, remember the graph has to cross the asymptote, the horizontal asymptote. It's got to approach the horizontal asymptote. So it's going down. Well, somewhere it's got to turn around and come back. Okay? So it takes a little bit of a, you have to really think about what it is you're drawing. All right. If that's it, yep, that's the last one. So, again, hopefully you're in class, because it's a lot easier to explain this in person where you can ask me questions. But if you have any questions, let me know. Consuelo, everybody.